All right. Do you guys remember how we determined the degree of a function?
It's the exponent.
Yeah, so the degree. What is the degree of a polynomial function? It is the highest exponent. So how does the degree affect the overall shape of the graph? So what does a linear graph look like? Straight line, right? And this equation would be y equals x to the 1 power. We typically don't write the 1, but that's what the degree really is for that one. What does a quadratic look like? It's a U shape, right? And what's the exponent on a quadratic? Y equals x squared. And then I could also do one that looks like this. And that would be very similar. We would say this is like y equals x to the 4th. So any even exponent that we have, the shape of the graph would be very similar. It would just make it skinnier because the y value would increase faster each time. So if I plugged in 1, 1 to the 2nd, and 1 to the 4th are the same. But if I plugged in 2, 2 to the 2nd is only 4, 2 to the 4th is 16. So the graph with the exponent of 4 would grow a lot faster. What does a cubic graph look like? You guys remember? Yeah. It's a squiggle. So it's like half a parabola going up and then half a parabola going down is what it looks like. So this would be like y equals x to the 3rd. If I did y equals x to the 5th, it would be a very similar shape. It would just be a lot steeper because it was growing faster. So down here where it says end behavior, the end behavior of the graph just means which way are the arrows going, okay? So the end behavior is which way the arrows are going. So we have two options. The linear graphs and the cubic graphs, these are considered to be odd functions because they have an exponent of 1 or an exponent of 3 or an exponent of 5 or 7 or 9, some odd exponent. And odd functions have arrows that go opposite directions. One goes down, one goes up. You guys see that for odd functions? Okay. So I'm going to say for the end behavior, we could have an odd exponent. And these particular graphs, the way that I drew them, I drew all of them as the positive version of the graph. So this is a positive x, so it goes from down to up. This is a positive x to the 5th, a positive x to the 3rd. So if I have an odd exponent and a positive coefficient, do you guys remember what a coefficient is? Yeah, it's the number in front. So if I have an odd exponent and a positive coefficient, then for my graph, my arrow is going to go down first and then up. So I can see this arrow goes down first and then up right here. Over here, this arrow goes down first and then up.
Are we looking down to up or left to right?
We're going from left to right. So this one went down to up. If you look from left to right, it goes down to up. If you go from left to right, it goes down to up. Now, if I take this exact same graph and I draw the negative version, so I would say this is y equals negative x. Or over here, if I draw the negative version of this one, y equals negative x to the 3rd, then what does that do to my end behavior? I'm not from down to up anymore. I'm up to down now. So if we have an odd exponent, but a negative coefficient, then we're going to say we go from up to down. All right. So next we're going to look at quadratics. So any function or just any other function that would be even. So x to the second, x to the fourth, x to the sixth. So this is an even exponent. And what do you guys notice about the end behavior on this one? Yeah, they both go up, yeah. So when an even exponent or an even function has a positive coefficient, the end behavior shows that both arrows go up. And then what happens if I take that parabola and flip it upside down? Yeah, both arrows would go down. So if our exponent is even still, but we have a negative coefficient now, then I'm going to say my end behavior is that both of the arrows go down. Okay, go ahead and take out a sheet of notebook paper. Okay, do not say it out loud, but on your paper, I want you to write down whether you think this graph is even or odd, and if it has a positive or a negative coefficient. So even or odd, and then you're going to figure out if it's positive or negative. You do not have to draw it, you just have to write down your prediction. So based on what you see from the arrows, is it even or odd? And is it a positive or is it a negative graph? Yeah, you can write number 1. All right, what's our prediction?
Odd and positive.
Odd and positive. Do we agree with Laura?
Yeah. But I guess.
Okay, so how, Laura, can you tell me how you knew it was odd?
Well, from the graphs that we just did, we did the odds first. Well, I we did the odds first, and it was arrows were from right to left. So I knew that it had to be odd. Yeah, so the first example.
Okay. So if you compare the arrows from the first one we did, you can see that the first arrow goes down and the second arrow goes up. Okay. All right, here's the next one. Do not say it out loud. Write it down on your paper. So what is our prediction on this one? I heard even and negative. So how did we know that it was even?
Because they're both going down.
Yeah, so the arrows, if the arrows are opposite ways, then we know it's odd. If the arrows go the same way, it's even. So they both went down, that's what tells us it's even. And then since they both went down instead of both going up, then we decided that the graph was negative. Okay, here's the next one. So what's our conclusion on this one? Odd negative. Is it odd negative?
Yes.
Yes. How do we know?
Because the arrows are going opposite ways.
Opposite ways.
They go up first.
Up first, then down. All right. I see a lot of people with headphones in, and I know that's not or that is inappropriate, so we should not have those. All right. Let's look at this one. All right, what's our conclusion? It's odd and it's negative. Good. Here's the next one. What's our conclusion? Even and positive. Okay, here's the last one. The last one was even positive. And then go ahead and write down this one. Alright, what did you guys conclude? Odd and positive. Okay, here's what we're going to look at next. We're not going to look at a picture, we're going to look at an equation. Alright, so when you look at this equation, can somebody tell me what the degree is? 4. The degree is the highest exponent. So this equation has a degree of 4. Is this equation positive or negative?
It's negative.
It's negative because the coefficient that goes with the x that had that exponent was a -5. So this is a negative graph. So go ahead real quick. Don't say it out loud, but write down what your arrows would be. So don't say them out loud, just write them down. What would your arrows be? So we have an exponent of 4. The graph is negative. So what arrows should we have? Down. Down, down. Because it's even and it's negative, so they should go down, down. Okay, here's the next one I want you to think about. So don't say anything out loud. I just want you to think about it and see if you can figure out what the degree would be and if it's positive or negative. So y equals x plus 2 times x minus 1. So in this one, can we see the highest exponent in this one like we could in the other one? No. So what do you have to think about in this one? You have to think about, what would happen if we multiplied it out? So does anyone know what the highest exponent would be if you multiply that all out? 2. Yeah, it'd be an x squared. So it's a foiling problem. I don't actually have to foil it. I just have to know what would happen if I did foil it. And I would get an x squared. So what is the degree for this one? 2. And then are you able to tell if it's a positive or a negative equation?
Yes.
It's positive. How do you know it's positive?
Because the x is positive.
Yeah, if you look at these, if you consider these two x's, if you were to multiply them together, it'd be x times x is positive x squared. You'd end up getting a positive number. So those are positive. And so which way should your arrows go? Up. Up, up. Okay. So I want you guys to keep that stuff in mind. We're going to do a few more problems on that page just to make sure we understand how to think about these equations. So, does anyone know what the highest exponent on number 3 is? 7. So they wrote it out of order. So degree of 7. Is it a positive or a negative? It's a negative because there's a -8 that's in front of that x. So this is a negative graph. So which way should the arrows go? Up and then down. Good. Up, down. All right, number 4, you have to think about it. Is that question? Up, down. So that just means that if we were to look at the graph, since that's an odd exponent and a negative graph, we're saying that it would look something like this if you were to draw it. And so we're saying it goes up first, then down. Yeah. All right. So for number 4, we have to think about what would happen if we multiplied it out. So when you multiply this out first, you'd have to think of x minus 1 times x minus 1. And I'm not going to do all the math, but I am going to say the first part is x squared, right? Yeah. X squared, and then there's some sort of number in front of the x, and there's some sort of number there. And then after we got that, then we would have to multiply by the x plus 5.
And then there's
And what would happen if I did that?
x to the third.
X to the third, and then plus stuff, right?
And there's a negative in front of it.
And there was a negative in the front of the problem. And so there would be some sort of negative that we would then have to distribute to the whole thing.
So it's all just negative, like plus.
So we're going to say that this degree is 3. And we're going to say that it's an even equation, or sorry, it's a negative equation. I said even, but I meant negative. Because of that minus in the front. Okay? So on these, you kind of have to think through how it would work. So how should the arrows go on this one?
Up, down.
Up, down. Okay. So the equations that are the easiest to find the end behavior on are going to be these equations that are written in standard form, where the exponents are in order, and you can just look at the first one and look at the exponent and say the degree, and then look and see if it's positive or negative. Those are the easiest ones. This one is almost in standard form, it's just kind of in the wrong order, so you have to look a little bit harder. And then these ones with the parentheses are in factored form. We call it linear factorization, and those are the ones you have to be careful of, because you really have to think about what the highest exponent would be. Okay, so we're going to go back to these notes now. All right, so underneath, I want you to write that the multiplicity, this is a new word, multiplicity is the degree of each root. The degree of each root. The multiplicity is the degree of each root. So, on the side of your paper, we're going to write x-intercepts are the exact same thing as roots, and those are the exact same things as zeros. Those are 3 different words that people use to describe where the graph would cross the x-axis. And when we talk about x-intercepts and we're doing graphing, somebody would probably call them x-intercepts. If you are using the quadratic formula to find the x-intercepts, people would probably call them roots because you're taking the square root often, so they might call them roots in that scenario. Are you listening? When we found them on the calculator, we called them zeros. If you remember how to find these on the calculator, you do second trace, and option number 2 is zeros, and they're called zeros of the graph because they're where the y-coordinate is 0. So these are 3 different words that mean the exact same thing. It just means where does the graph cross the x-axis. Okay? In this situation, if we keep having talking, you guys are just going to sit out in the hall. In this situation, they tend to call them zeros or roots. So in your mind, just think, oh, that just means x-intercepts. All right? So for us to look at this particular equation and find the x-intercepts, we just have to see what would make each factor equal 0. So the x-intercept right here would be 0. The x-intercept right here would be positive 3. And the x-intercept right there would be negative 5. All right? So we have x equals 0. X equals positive 3, x equals negative 5. So those are each of the roots that we would see for this equation. And then for each of those, we have what we would describe as the multiplicity of each root, which is very similar to what we would think of when we think of degree. It's just the highest exponent for that root. So this x right here does not have an exponent, so we would normally put a 1 there. And so for x equals 0, I'm going to say that that has a multiplicity of 1. X minus 3 is to the second power, so I'm going to say that x equals 3 has a multiplicity of 2. And x plus 5 to the third has a multiplicity of 3.
So this is is just a way to make the factored form easier to figure out.
Yeah, basically. So the multiplicity is the degree of each root. We're going to say the degree of the equation is the multiplicities all added up. So if we wanted to think about what would happen if we were to FOIL out this whole equation, like write out x and then x minus 3, and then x plus 5, x plus 5, x plus 5, if we were to write those all out and like multiply the whole thing out, the way that we can see what our highest exponent is, we can add up these multiplicities. So 1 plus 2 plus 3 is 6. So we're going to say that this equation has a degree of 6. That's what would happen if you multiplied out the whole thing. You'd get x to the 6th power. And then if we want to determine if it's even or odd, we just have to look in the very front. So what do you guys see in the very front? Is there a negative there? No. Nope, there's no negative. So we're going to say this is actually a positive equation. So we looked to the front to see if it was positive or negative. So the degree tells you the shape of the whole graph. So we can say that a shape of the whole graph has an overall shape like this, where there might be some stuff, some extra squiggles happening in the middle, but overall I know this is even and negative, and so I can see that overall this is a U-shaped graph. You guys see how it's a U-shaped graph going down? It just has some weird stuff happening in the middle. Or I can look at this one and say overall this is odd, so I've got an arrow going up and an arrow going down, and there's lots of squiggles in the middle, but overall it has that shape. Multiplicity is kind of like if you zoom in and look at just the x-intercept. So I'm going to ignore everything else and just look at what happens at that x-intercept right there. That's what the multiplicity tells you. So we can also say that the multiplicity have these same different shapes. So if we have a multiplicity of 1, and here is like an x-intercept on the graph, then a multiplicity of 1 is kind of like a linear function. And so we would say at that x-intercept, it would go straight through the x-intercept. That's what a multiplicity of 1 looks like. So we're saying if you zoomed in on the graph and just looked at what was happening at that one x-intercept, you'd see the line growing straight through. Now lines don't always go straight through slanted up. Sometimes they go straight through slanted down. And overall, that's all considered multiplicity of 1.
So if it curves a little, like when the x equals 3,
yes,
it's a multiplicity of 2, so it would curve a little at the x.
Yeah, so if we look at this one, a multiplicity of 2 would have either a parabola sitting on top of the x-intercept or a parabola coming up from underneath the x-intercept. And then a multiplicity of 3 would say it's going through the x-intercept still, but it curves as it goes through the x-intercept. It doesn't go straight through, it curves on the way through. So that's what multiplicities of 3 would look like. And they can go up to the right as they go through, or they can go down to the right as they go through. Okay, so we're going to go ahead and draw, and you're actually going to draw a sketch of this. Do you guys have room on your papers, or did you write as big as I did? Some of you guys did. So you can draw this on this paper, or you can put it on your notebook paper. Either one is okay with me.
So are these like transformations, or
They're not transformations. These equations will not have transformations, but these are like the special characteristics that we look for that will help us. Like today we're going to recognize them, we're going to look at the graph and be able to see them. Tomorrow we're going to use them so that we can draw our own graphs. Yeah. Okay. So go ahead and copy that graph. Be really careful to make sure you draw it looking the same. So here is, I've got an x-intercept right here at -3, and I have an x-intercept at 0, and I have an x-intercept at 2. And then be real careful to make sure that as you draw it, it has the same shape as it goes through those x-intercepts. Okay, so we have an x-intercept right here. What is the x-intercept right there? -3. So what would we expect to see inside the parentheses? +3, right? So I'm going to write x plus 3. And if you look at this, it goes through the point, but it squiggles as it goes through the point. So would that be a multiplicity of 1, of 2, or of 3? Multiplicity of 3. So that exponent is going to be a 3. Right here we have another x-intercept, and that's on 0. So if you have parentheses, what would parentheses look like if you had an x?
It would be outside. It would be x on the outside.
Yeah, it'd be x on the outside. If you like to have parentheses, you can always write x plus 0. That would be fine. So you can do x plus 0 or a plain old x. It's up to you. And does this look like a multiplicity of 1, a multiplicity of 2, or a multiplicity of 3? 2. It's a little parabola sitting there on the point, so that's a multiplicity of 2. If you guys notice, I do not care what's happening down here. Do you guys see how I completely ignored this part of the graph? I only care where it crosses the x-axis. Those are the only parts of the graph I'm looking at. Okay. So over here, this is another x-intercept. And this is an x-intercept at +2, so what should be in my parentheses? X minus 2. And if you look, what multiplicity is that? 1, 2, or 3? It's a multiplicity of 1. Okay, so after that, we can go ahead and write our equation in y equals form. So I'm going to say y equals, and then I put those parentheses next to each other. I'm going to write x minus 2. Most people would take this plain old x and would move it to the front, x squared, because most people would not put it in parentheses. If you put it in parentheses, I will not mark you wrong. You're right. People will just look at you a little bit funny, but that's okay. All right? So that's a good answer. Or if you want to say x plus 3 to the third, x plus 0 squared, x minus 2 to the 1, that would be fine as well. Now, based on the arrows, what type of degree would you expect this graph to have? We got up, up. So we would expect it to be positive, and what would we expect it to be, odd or even? Even. So we would expect this to be even and positive. So if we look, we want to count our multiplicities up. So I have a multiplicity of 3, and a multiplicity of 2, and a multiplicity of 1. And what happens? Degree of 6. Does a degree of 6 fit our picture?
Yes.
Yeah, it does. 2 up arrows, that fits. And then if we look at our equation, so we already know that our degree matches the picture. Degree of 6 makes sense with the picture that we could see. Does our equation make sense if we know that this graph is supposed to be positive?
Yes.
Yes. So we're going to say that both of these are good answers, and you could use either one.